Okay, this is the second video lecture for general physics for the lecture that would have been given yesterday, March 18th. And this is where I'll do the examples. And here's our first example. This is different circuits containing capacitors and resistors. And the question is, if you start with a circuit that is charged up, the capacitor is charged up to a voltage of 5 volts, and then you close all the switches and you see what the highest voltage is after 1 second. Okay, and so A, we have a capacitor that is at 1 farad and a resistor at 2 ohms. B is 0.4 farads and 2 ohms. C is 1 farad and 3 ohms, and D is 0.4 farads and 3 ohms. And you can tell from the equation, if we go back to this previous slide, you look at this equation, you can see that the amount of time and the inverse relationship between resistance and capacitance is going to take that exponent on E, and it's going to make it smaller in the negative direction. That means if it's smaller in the negative direction, then E is going to decrease more slowly the higher the resistance and the higher the capacitance. So the answer, I'm going to switch over to DocCam so I can show you. I did 2 of these. I did A and then I did C. I went ahead and did the calculation just to show this. So let me do DocCam. Okay, here we go. Make sure it's in focus, which it's not. There we go. So here's our governing equation right here. V is the voltage of the capacitor. V naught is the initial voltage of the capacitor, exponent negative T to the resistance and the capacitance. So if you look at A, this is option A, then we start out with an initial voltage of 5 volts, E to the negative time, which is 1 second, divided by 2 ohms, divided by 1 farad. Okay, you work out the math there, you just take the exponent function, and that gives you 3.03 volts. So make sure that you try that. I don't know what character map is up here, that's bugging me. Okay, 3.03 volts. Try that on your calculator and make sure you get the same number. Now C looked like a better option with a resistance of 3 ohms and a capacitance of 1 farad. So our voltage here is 5 volts. That's our initial voltage, E to the minus 1 second, divided by 3 ohms, divided by 1 farad. Okay, and so this number, this denominator is larger. That makes this a smaller negative number, and E decays more slowly. Okay, so that gave us a voltage of 5 volts times E to the negative 0.33 power, or 3.59 volts. And that would be the highest voltage. So that's C on the previous problem. So I'll go ahead and switch back to that. Okay, so C is the answer. Now we went, I promised you in the previous video, or I think in the previous video lecture, I said that was wrong. And so I want to show you something on the DocCam regarding the right representation of capacitance and resistance in myelinated axons. Okay, so let me switch back to DocCam and I'll see if I can get this. So this is in your book. This is page 751. And if you look at the electrical model of a myelinated axon, oops, I lost my pen. I need a pen. There's a pen. Okay, so if you look at the myelin sheath here, the thickness of the myelin sheath is very important for the capacitance, okay? And the capacitor, the myelin sheath, the membrane in the myelin sheath serves as the capacitor. The conducting fluid in the axon serves as a resistor, and the ion channel right here serves as a little battery. Okay, so what happens is as this battery gets charged by the previous capacitor, then that flows current and that charges this next capacitor. And if that capacitor can charge quickly, then that will cause the nerve to fire in a much quicker fashion. All this happens in the millisecond range. And so then the different nodes of the axon can fire very, very quickly and can work down the chain. Okay, so when this happens, this voltage is turned on. It immediately charges that capacitor. So we want that capacitor to charge very, very quickly. So if it charges slowly, then we have a real problem. Now, this membrane is thick, so the membrane represents the distance between the two plates in the capacitor. So if we go back to chapter 22, we can look at capacitance, chapter 21. We can look at capacitance and see that capacitance is, oh, DocCam, help me. This is page 687. Okay, capacitance is inversely related to distance between the plates. Okay, so if the distance between the plates is large, then the capacitance is small. If the distance between the plates is small, capacitance is large. Okay, so what that means is when we get to the example here, that if we have thinning of the myelin sheets, then the distance between the capacitors plates is small and the capacitance is large. And with a larger capacitance, it will actually take longer to charge up. With a smaller capacitance, it will take less time to charge up. Okay, so when we have that situation, so thinning of myelin sheets is going to cause your nerves to fire more slowly, and nerve conduction will be more slow and sluggish. But if you have thicker myelin sheath, then you will be able to charge up your capacitors more quickly, and that axon will fire down the different nodes in a much quicker fashion. So I hope that helps. So if we look at the next example, so let's say we have a myelinated nerve fiber. It has a conduction speed of 55 meters per second. If the spacing between the nodes is 1 millimeter and the resistance of the segments is 25 mega ohms, what is the capacitance of each segment? Okay. And just to let you know, a good representation of the time constant tau is a good estimate of how long it takes the signal to jump to an adjacent node. Okay, so let's look at that really quick. So here, if I switch over to the document camera, you can see the tau. Let me get my magic pen. It's one of these equations in your book that they didn't number, so you lose it. Tau is equal to resistance times capacitance. So if we know tau and we know resistance, then we can calculate capacitance. Okay, so let's go ahead and do that. A fresh sheet of paper and my magic pen. So we know tau is equal to RC. We know that tau is time to move 1 millimeter in nerve. Okay, we know that resistance R is 25 times 10 to the 6 ohms. That's just 25 mega ohms. So then we also know the velocity of a nerve impulse is, I'm going to call it VEL, not V, because V is voltage. So velocity is 55 meters per second. Okay, so if the nerve impulse can move at 55 meters per second, then we can take the reciprocal of that and we can find how many seconds it takes to go 1 meter. Okay, so in other words, I get my calculator and I calculate that out. Just take 1 divided by 55. And that gives us the time for 1 meter as 0.018 seconds. Okay, so if that's the time that it takes 1 meter, then the time to take 1 millimeter is equal to 0.018 seconds divided by 1,000 millimeters per meter. Okay, so that time is 1.8 times 10 to the negative 5th seconds. Okay, so now we have the time that it can move 1 millimeter, that as we reflected up here, that's equal to tau. Okay, so we know what R is and we know what tau is, and so we know that tau is equal to RC. So capacitance would just be equal to tau divided by R, and that would be equal to 1.8 times 10 to the negative 5th seconds divided by 25 times 10 to the negative 10 to the 6 ohms. Okay, so capacitance you see is going to be a fairly small number. And that gives me capacitance of 7.3 times 10 to the negative 13th farads. Or, that's in the picofarad range, so we could say that that is 0.73 picofarads. Okay, so that is the capacitance in one node, and that answers that particular question. So we can go back to PowerPoint. Okay, on our learning check. And yay, that concludes chapter 23. Next, actually tomorrow, which is the 20th, when your homework is due for chapter 22, I'll send out an email via Moodle that gives you your homework for chapter 23. Hope you have a good day.